Before we get into the main topic today, which is Boltzmann factors, where they come from and how we use them, I wanted to answer a question from Piazza because it's a very good question and it relates to something that I maybe didn't explain in enough depth in the last lecture. And that's the difference between large and very large numbers. So you're accustomed from other physics courses to doing perturbative calculations. And what I mean by that is you say, okay, here's the velocity is such and such. I've calculated that from the main effect that I'm considering. And you say, okay, on top of that, there's some very weak friction, but that's only 1% as strong as what I did for the original calculation, so I can just add that in as a perturbation, right? Or maybe drop it entirely, depending on whether you care about 1% precision or 10% precision. So we're going to do something similar in StatMech, except we usually are looking at the logarithms of numbers. And so it's going to look a bit different, even though, in fact, we're doing essentially the same thing. So when I talk about a large number, this is something like the number of atoms in a chunk of stuff. So think Avogadro's number size numbers. So these are very large. When I take the logarithm of a very large number, I get, sort of a normal number, right? If I take the logarithm of Avogadro's number, I get something around 100. If I take the logarithm of 2 times Avogadro's number, okay, I can separate that out into the log of Avogadro's number plus the log of 2. The log of 2 is less than 1, so it's less than a 1% perturbation on top of the logarithm of Avogadro's number. So by normal perturbation theory, you would think, I can drop that. That's small. It's less than 1%. The thing that makes it look different in statistical mechanics is we frequently work with the logarithms and then go back to the actual number itself. So if I take 2 times Avogadro's number, take the logarithm, drop the small piece, which is the 2, and then go re-exponentiate, I get Avogadro's number back. And when you look at that and say, whoa, geez, that's half as big as it was before, right? You dropped the 2. The point is that when we're working with large numbers, frequently factors of small numbers are irrelevant. Again, because physically we're frequently taking logarithms. Now, Schroeder makes a nice distinction here between large and very large numbers. Avogadro's number is large. E to the Avogadro's number is very large. Okay, so a very large number is something that when we take its logarithm, we get a large number. So for a very large number, we may drop a factor out front that's a large number because when we take the logarithms, the logarithm of the very large number will be a large number and the logarithm of the large number will be sort of a regular sized number. So again, there's going to be a separation of scales there, right? If I have Avogadro's number times e to the Avogadro's number, when I take the logarithm, this will be log of Avogadro's number, which is about 100, plus the log of e to the Avogadro's number, which is Avogadro's number. And when you see it in that sense, you'd say, well, 100 plus Avogadro's number, why on earth would I care about the 100? Like, throw it away. It's so tiny. But when you exponentiate, that means that you've dropped a factor out front. And it may even be a factor that's a large number because it's multiplying a very large number. Okay, so it's a bit, I suspect it's still going to feel a bit funny even though I've told you, oh yeah, it's totally fine. So let's go through how that impacts this question on Piazza. So the question on Piazza was, in the previous lecture, we wanted to know the number of states when we have 2 Einstein solids stuck together, each one with n over 2 oscillators. And the question is, what's the number of states as a function of the way you split their excitations? So the total system has n oscillators and q excitations. We were assuming that q is much bigger than n. That's helpful. It makes math a bit simpler. And what we got to in the end was this expression. Okay, so this expression has a prefactor out front and then this Gaussian term. And the Gaussian term is what told us that, hey, when QA, just the number of excitations in solid A. The two pieces were A and B, right? When the number of excitations in A is Q over 2, in other words, half of the excitations are split evenly, then this Gaussian term becomes a 1. That's the maximum. So the maximum number of states is when half of the excitations are on one side and half on the other. Now, what is that maximum number? Well, the maximum number came out like this, which is QE over N, all raised to the N. And the question in Piazza was, hey, wait a second, that's the expression for the total number of states, as in with any number of excitations on either side. So we've got Q total excitations. If you add up all the ways that you can split them up, including half and half, but also, half plus 1, half minus 1, 3/4, 1/4, all of these together, this was the total number of states. And so the question asked, how does that make sense? You said the maximum number comes when they're split evenly, and it's this. But that's also what you get if you add up all of them. So how does that work out? Okay. And the answer comes back to this large versus very large numbers. So that does, in fact, sound a bit funny. The difference comes because this is correct to within a factor of a large number. Okay. So how can we see that? Suppose you had this and you just sort of threw a normalization constant out front. You said, wait a second, I know when I add these up, it has to be this. So it's got a Gaussian form, but I must have messed something up. Let me fix it. And now you would be adding these up, right? QA is 1 plus QA is 2 plus QA is 3, da, da, da. But since we're working with very large numbers, that sum is going to look an awful lot like treating QA as a continuous variable and taking the integral. So I've just reminded you here, because we talked about this at the end of the last lecture, when you integrate a Gaussian in standard form, this is the result. So if I integrated this Gaussian to get the total number of states with any splitting for QA and QB, it'll add an extra factor of 2 pi sigma squared. Sigma squared comes out of here, right? So sigma squared is, well, you want to rewrite this as 4n over q squared, all of that times a half to get this 2. So sigma squared is q squared over 4n. If the integral would give you a term like this, then put 1 over that term out front. Now it's normalized. So now if I integrate this whole thing, I will get just this term. And so now it would agree with our previous calculation that said, oh, the total number of states for an Einstein solid with n oscillators and q excitations is just this thing. Okay. Now all I've done is flip this around and sort of reduce this. And what you notice is this answer and this answer differ by this term. And this term, square root of 2n over pi q squared, is a large number. It's not a very large number. Whereas this guy, the prefactor that tells you, this sort of the total number of states, that's a very large number. And so in fact, these two answers are equivalent to within a large number factor. And since they're both very large numbers, for our purposes, we'd say this is good. This is all we needed. This is equivalent to this. Now that sounds strange because this n could be, Avogadro's number size. And taking a square root means it's still trillions, right? Q is even bigger. So if we've got q squared, okay, these are really big numbers. But I got to be careful. They're large in the sort of in the way that we're describing this. They're large, but they're not very large, right? This may be on the scale of 10 to the 23, but this is on the scale of 10 to the 23 raised to the 10 to the 23. This is humongous. Okay, maybe the stuff inside is smaller. Maybe Q and N are equal and this is just E, but it's still E raised to the 10 to the 23. So this is just fantastically larger than this. Okay, now that may not totally satisfy you, and if it doesn't, great, because we're going to go through the calculation slightly more carefully. So all of this comes basically from the fact that when we did this calculation originally, we used Stirling's approximation as n to the n e to the minus n. Okay. There's an extra factor, which is square root of 2 pi n, that we ignored. And we ignored it because we know n is a large number, which means n to the n is a very large number, whereas the square root of 2 pi n is just a large number. So now what I want to do is go back and do this derivation with all of the large number factors intact, and you'll see we get exactly the same result that we would have gotten by just sort of arbitrarily throwing in the correct large number up here, saying, well, we know what the answer should be. It should add up to that, so let's put it in. Okay. So now if we do this more carefully, we're going to say the total number of states when we have q excitations and n oscillators. Remember, it's this combination, q plus n minus 1. Choose n minus 1. And previously we said, we can get rid of these ones. These aren't important. But that's because we were assuming that we only cared about very large numbers, right? If we care about large numbers, we have to be a bit more careful. So q plus n, choose n, differs from this by a factor of n over q plus n. If q is much bigger than n, then this could in principle be a large number. It's certainly not a very large number. We're not taking n factorial or e to the n, nothing like that. But it's a large number. So when we want to keep track of large numbers, we have to be a bit more careful. Great. Now we're going to do this combination using Stirling's approximation, but including the square root of 2 pi n term. Okay. So here's this prefactor. We've got for q plus n factorial, it's q plus n to the q plus n times e to the minus q plus n. So here's a cute trick. Just make it q plus n over e, right? You were going to have e to the minus q plus n out there. Just put the e inside. Saves you a little bit of writing. Okay. So that's what we would have done before. That's the very large part. Now we keep the large part. Square root of 2 pi times q plus n. Same story for the factorials in the denominator, right? If it's q plus n, choose n, we're going to have a q factorial, q over e to the q, square root of 2 pi q, and we're going to have the n factorial, so n over e to the n, square root of 2 pi n. Multiply all of this stuff together, do it on a scratch sheet if you like, and then come back, and what you'll see is we get this form. So it's q plus n over q raised to the q, q plus n over n raised to the n, and then the square root bit. Okay. So now we have done the calculation including the large factors. When we do it including the large factors, what will we get when we say I don't need omega of qn? So that's the total block, all the possible states of the total block. What I want is to split into two blocks and give each of them q over 2 excitations. What's the number of states in that system? Okay. So for one of the blocks, we just take this and make it q over 2, n over 2. And what you'll see is these first two terms, nothing changes except the exponent. It just becomes divided by 2, right? We've got q over 2 and n over 2 divided by q over 2. All the 2's go away. Same story here. So there's just the 2's and the exponents. Things change a little bit in the square root because you've got two terms that'll be halved and only one on top. So we lose this 2. Okay? But the number of states for the system of 2 stuck together is this number times itself, right? This would be the number of states in A. We have the same result for the number of states in B. The total system is the product. So when we take this and square it, okay, now we see the key difference. The stuff out front, it only differed by the exponent, and when we square, we multiply the exponent by 2. We're right back to where we started up here. So if you only keep track to within very large numbers, same result that I had in the last lecture. This thing equals this thing. The difference comes in the large factor. So when we square this, we're going to end up like so. And when we compare it to the result up here, okay, what we're going to see is that this is the difference, or rather the ratio. Okay, difference in the logs, the ratio. So the number of states in the evenly split system is equal to the total number of states times this factor, which is n over essentially q squared, because we're going to look in the limit where q is much bigger than n. But this factor is clearly less than 1 because n is large, q is large but much bigger. So it's n over q squared. This is less than 1. So now we do get the result that you expected, which is that the number of states with excitations evenly split is smaller than the total number of states, sort of summed over any way that you split the excitations. Now the factor that differs is here, and we want to compare it to this guy up here. The reason it doesn't look exactly the same yet is that our original calculation was in the limit where q is much bigger than n. So let's do that. If I take this result from here, this guy, and now I'm just going to pull the factor of q out of here. Okay. So that's going to give me q over q is 1, n over q, right? And now I'm going to rewrite the exponent in a funny way. Instead of q, I'm going to write it as q over n times n. Okay. Hold on to that. We'll come back in a second. Here, just divide again. You've got q over n plus 1. In the limit that q is much bigger than n, this will be much bigger than this, so we'll end up dropping the 1. And then down here in the denominator, sort of similar story. Pull the q out, you get a 1 plus n over q. If q over n is much bigger than 1, n over q is much smaller than 1, so we'll end up dropping this term. Okay, so now, in the limit as n over q goes to 0, this thing that's inside of the bracket, this is a representation of E. Okay. So this hopefully is something that you saw in calculus maybe many years ago. Maybe it's a fuzzy memory. The limit as x goes to 0 of 1 plus x raised to the 1 over x equals E. So if that's not familiar, maybe play around with it, do some numbers, use 0.0001 for x, see how close it looks. But I will tell you that's the case. So we get E in this, raised to the n, e to the n. The q over n is much bigger than the 1, so drop it. The n over q is much smaller than 1, so drop it. Put it all together. This is our final answer in this, again, high temperature limit, which is what we were doing in the last lecture. And now when we compare this expression to the expression up here, right, we see we've got the same term popping out. So this differs from the total, again, by this factor that we guessed before by saying, well, we want the Gaussian to be normalized, so we probably need to drop an extra factor in here. It turns out that's exactly the factor that we needed. And just to recap the story again is they look different because they differ by just a large factor. And in our original calculation, we were dropping large factors. We were only treating very large numbers. Now, this also points out something, which is that the number of states when you split the excitations evenly is a very large number. This large number essentially is the width of the distribution. Remember, we did this calculation in the last lecture so that we could see that the distribution for number of states is very sharply peaked, right? We're going to have we're only going to fluctuate around this close neighborhood. Well, the size of the neighborhood in some senses is large. It's a large number, but it's not very large. So I hope that helped. And again, definitely, I really appreciate the great question on Piazza. And if there's still confusions about this, definitely jump in there and we'll have some more back and forth about it. Now we're going to move on to the main topic for the lecture, which is probability and statistical mechanics. So very quickly talk about what we mean by probability, though I assume this is mostly review, should be things you already know. And then we'll talk about the main structure that we're using, at least for the next couple of weeks, to calculate probabilities, which is something called a Boltzmann factor. So we'll talk about where it comes from and then a little bit how we use it. Next lecture, we'll go into much more depth in how it's used to do calculations. And all of this material is connected to section 6.1 in Schroeder's book. So again, if things are not totally clear, certainly ask questions in Piazza, but also check out Schroeder, because he will discuss things maybe slightly differently than I do. Maybe the way he says it gets you better than the way I say it. So that's the book. So with probability, what I've written here is essentially, again, hopefully things you already know about probability. If I have some event, which is a nebulously defined word in this context, some event A, and I want to know what's the probability of A, it's just the ratio of the number of ways that A can occur divided by the total number of ways that any event could occur. Okay, so again, using this event term, it's a little funny, so let me just be very concrete. If I'm flipping a coin, right, the probability of heads is the number of ways to get heads, which is 1, divided by all the different things that could happen, which is heads or tails, so 2. Probability of getting heads is a half. That should sound familiar. Okay, similarly, if I roll a 6-sided die, not one of these fancy 20-sided ones, just the good old 6-sided die, the probability of getting a 5 is the number of ways this event can happen. There's one way, lands with 5 pointing up, divided by the total number of ways that it could happen, which is 6, right? Any of the 6 sides of the die could land up. Okay, slightly more complicated would be if we're going to flip a coin 100 times or flip 100 coins once, either way. And the question would be, what's the probability we get exactly 50 heads and exactly 50 tails? Well, the number of ways that can happen is going to be a combination, right? So we're going to take the 100 events that we've got, 100 flips, choose 50 of them to be heads. Then the other 50 must be tails. The total number of ways that this can end, it can either be heads or tails for each of the 100 flips. So it would be 2 to the 100th power. So the probability is this rather unwieldy looking thing. Of course, you know, we could go and do Stirling to deal with this, but we won't do that now. We've done a lot of Stirling already this lecture. Or if I roll 2 dice, okay, what's the probability that the sum equals 7? So if I roll 2 dice, say the first one lands on 1, there's a way to make 7 if the second lands on 6. If it lands on 2, you can make it with 5, 3, 4, 5. If you check all the way up to 6, if it lands on 6 and the other lands on 1. So there's 6 different ways to get a sum of 7. So number of ways to get sum of 7 is 6. And if you're rolling 2 die, there's 6 ways one can land, 6 ways the other can land. So the product is 36. So the probability is, well, 1/6 when you divide it out. Okay, very basic, like welcome back to probability here. Hopefully this is all very familiar. If it's not, again, please do ask questions in Piazza. I said I'm assuming that you guys have seen this before, but that doesn't mean that you have to have. So just let me know. But I do want to make one remark about probability in a more conceptual light, which is I gave you this definition here and said, yeah, it's the A is an event and the number of ways, and that all sounds a bit sort of fuzzy. One interpretation, and this is the interpretation we'll be using, is that probability tells you the frequency with which you will see that event in a very large number of trials, right? So if I ask the probability for heads, and the answer is 1/2, what that means is that if I flip 10 million coins, I'll probably get about 5 million heads, okay? Now I just said probably, so that sounds a little circular. I will get 5 million heads plus or minus some number, and I can actually continue deeper into statistics and say, what's that plus or minus? We will care about that eventually. That's a question related to what we calculated in the last lecture, which was not just the most likely value for QA, but also the width of the distribution for QA. But for the moment, let's not worry about how certainly we'll get half of them heads. We'll just say that if we do a very large number of trials, half of them will be heads. And similarly, if we roll 10 million die, 1 out of 6 of those, so 10 million over 6, what is that, 1.67 million of them will come up with a 5. Now, this is if this was, I need to flip a whole bunch of coins, this means I need to flip 100 coins a whole bunch of times. Or flip one coin very, very many times and divide it into sort of bins of 100. But I think you get the idea here. Just if I have a very large number of trials that I'm testing, the probability lets me know the frequency with which I should see specific results in that large number of trials. Now, that if you want to go down an extremely deep rabbit hole, that's called the frequentist understanding of probability. There's also a Bayesian understanding of probability that we won't need in this course, but if you find that you need, to kill an hour or possibly the rest of your life, you can spend quite a lot of time on that. So with that reminder of probability, now let's go and look at the probabilities of states. Okay, in the previous lecture we talked about counting and multiplicity of states. Now we want to put that to use and calculate probabilities. So the system, or the setup that we have in mind here, is some isolated system, S, so there's some wall around this through which nothing can pass, energy, numbers, pressure, nothing can pass through that wall. So our system is truly isolated. And now we want to break up the system into two parts. One we're going to call the reservoir, that's the big blue thing. And the other is a subsystem, which in this case I'm going to assume is a single atom. Okay, so that's A is a subsystem of the total system, and it's much, much smaller than R, which is our reservoir. Okay, right? Reservoir is a big thing that holds stuff. And in particular, what we're going to assume here is that A and R can exchange energy with one another. Okay, and this sort of subtitle that I've given you here, canonical ensemble, what that means essentially is we're considering a system where the reservoir and the subsystem can exchange energy, but not particles. Okay, so the total multiplicity, total number of states for the system, is just the product of the reservoir states and the subsystem states. Now, what I would like to do is fix the state of the atom, right? So let me step back. The goal here is to calculate a probability distribution for states of the atom. So I've got an atom, it's got a ground state and different excited states. We can talk about how many excited states we want, but just assume it's got some finite number of states. And we want to be able to calculate the probability that we find it in any one of these given states. So the way that we'll do that is by fixing the state. Say, well, let's make the state this. And calculating now the multiplicity of the total system when that's the state. And then we'll say, okay, we can do this for any state. We can use that to get the total multiplicity. And if we have multiplicity for one state and multiplicity, total multiplicity, that gives us a probability. Okay. So that's essentially what's happening in these next two lines. I'm going to fix the state of the atom. I'm going to call it state Si. Okay, S for state, I for whichever index we're using to count it. And we're going to fix omega A to be 1 by saying A is definitely in state Si. Okay, if we've completely defined the state, then the multiplicity is 1. that reduces the multiplicity of the entire system to just be the multiplicity of the reservoir. And I've said the multiplicity of the reservoir when the atom is in state Si, because that multiplicity will depend on the state of the atom. Now, why? Well, we've got an isolated system. So if the energy of the atom goes up, necessarily the energy of the reservoir goes down, and vice versa. Okay, so when we can write this all in terms of the multiplicity of the reservoir, we can say the probability that the atom is in state Si is exactly the multiplicity for the reservoir, right? Number of states the reservoir can be in when the atom is in state Si, divided by the total number of states. Okay? And since I don't even have a good symbol for this, I've just written total omega, we probably want to get rid of that. Or maybe you can think of it the other way. I don't want it around. I didn't even bother to give it a good symbol. What we can do to get rid of this is to take ratios of probabilities. And so that's what we're doing in the next line. We say, look, I don't know what total omega is. I don't want to have to think about that. If I consider two states, S1 and S2 of the atom, then the ratio of their probabilities is the ratio of these things, and the total omegas will cancel out. So the ratio of the probabilities for these two states of the atom is just the ratio of the reservoir multiplicities for each of those two states. And now, to connect this sort of very just counting sort of idea back to thermodynamic quantities, we're going to use what we talked about in the last lecture, which is the entropy, something you talked about in thermal physics, is equal to Boltzmann's constant times the log of omega. And I realize we talked about Boltzmann's constant in the last lecture because we brought this up. So if you forget, though, let me just remind one more time. And now I've done two terrible things to you, which is I have written on a vertical surface, in which case my handwriting is awful. And I think there's a very real chance that I've written this underneath the video of me. But maybe those cancel out because I can make it look slightly less awful and then scroll it up where you can see it. Okay. And it still looks awful. Well, fine. So Boltzmann's constant, reminder, 1.38 times 10 to the minus 23 joules per Kelvin. Okay, so this is how we convert from log of multiplicity to entropy. So if entropy is the log of the multiplicity, we can go the other direction. Multiplicity is the exponential of S. So essentially just solve this for omega and plug it in. This ratio is e to the 1 over k times the entropy in the reservoir. So remember, we were looking at multiplicity of the reservoir. So now the quantity we end up with is the entropy in the reservoir when the atom's in state 2 versus that same exponential when the atom's in state 1. And of course, ratio of exponents is just the exponent of the difference. So this, we can now write the probability ratio as e to the 1 over Boltzmann's constant times the difference in entropy between the two states. Okay, and again, just to be totally explicit, the difference in the reservoir entropy when the atom goes from state 2 to state 1. Okay, so we're looking at the probabilities for the states of the atoms in terms of the entropy of the reservoir. Okay, so we've got this difference here. And now we're going to make use of the fact that the subsystem is much, much smaller than the reservoir. So this difference in the entropy for the reservoir, which I'm abbreviating as delta S, because the subsystem is much, much smaller than the reservoir, the change in entropy should be much, much smaller than the total entropy of the reservoir. And when that delta is very, very small, we can approximate it as a differential. And now we get to make use of all of these properties of differentials that you talked about in thermal physics, right? So when we take, normally in thermal physics, you'd see T times ds, right? You'd have some du is equal to, T ds minus P dv and so on. So we're just going to turn that around and solve for ds in terms of T, du, dv, dn, and so forth. And of course, you spend some amount of time doing things like Legendre transformations. If I have this as P dv, but I really want to think of it in terms of V dp, you can do the Legendre transformation and get to there with a minus sign. So in this form, we can now think about the multiplicity not in terms of entropy, which is sometimes sort of a hard thing to get your head around and certainly a hard thing to measure. We can think of it in terms of things that are easy to measure: energy, volume, number. Furthermore, because we have a closed system, the energy change in the reservoir is going to be exactly minus the energy change in the subsystem. Similarly, the volume change of the reservoir minus the volume change of the subsystem, the number change in the reservoir minus the number change in the subsystem. And so we just carry this whole thing across with a minus sign out front. And now these quantities refer to our subsystem. So we've made sort of two very nice improvements to our formula. One is we're now in terms of sort of more physically measurable things, energies, volumes, numbers. And we're now talking about these quantities with respect to the subsystem. In other words, the bit that we're looking at, right? If we say, what's the probability of a certain state in the subsystem, it's maybe a bit confusing to then have to calculate the energy or the entropy of the reservoir. Here we say, no, we're looking at the subsystem, and all we need to know is the energy change, volume change, these changes for the subsystem. Okay. So putting that all together now, we're going to make a jump, and the jump is sort of twofold. I've got three terms here. It doesn't look so bad, but we don't want even all three terms. So we're going to make an assumption that P dv is much smaller than du. Now, that might be, because you're in a totally fixed container and the subsystem can't change volume, but it could also just be that the energy content of the sort of work done is much, much smaller than the energy content for the change in internal energy. And so in this example of an atom, if an atom goes from its ground state to, say, its first excited state, that's a big change in energy. That's, big is always relative, right? So that's a change in energy of an electron volt, which is about 10 to the minus 19 joules. Those are both approximate, right? Depends on the atom, depends on the transition, but order of magnitude, it's around an electron volt or two, and that's on the scale of 10 to the minus 19 joules. Whereas the change in volume for the atom is extremely small, right? This is going to be 1/10 of a nanometer cubed, so something like 10 to the minus 30. If you're at a pressure of 10 to the 5 pascals, like normal atmospheric pressure, that 10 to the minus 5 times 10 to the minus 30, it's 10 to the minus 25. So this term would be about 1,000,000 times bigger than this term. And that's going to be true in a lot of cases, so this is something that we maybe need to keep an eye on, but this is a good approximation. We're also going to get rid of this term just by definition. We're going to say our reservoir and our subsystem cannot exchange particles. They can exchange energy, but they can't exchange particles. And that definition is actually why up here at the top I referred to this as the canonical ensemble. Okay? So canonical ensemble means we're looking at a statistical system where energy can be exchanged between reservoir and subsystem, but particles cannot. So this mu dn term, it's going to come back in a couple of weeks. And when we bring it back, it'll be a different ensemble. It gets a better name. It's called the grand canonical ensemble. But for now, we want to just deal with one complication, which is exchange of energy. So with those caveats, we can now get rid of these two terms, and in the end, we just have, so looking up here, ds would now just be minus du, just to say minus the difference in energy. And there's a 1 over t. Don't forget the 1 over t comes along for the ride. So the ratio of the probabilities is minus now, because we switched from reservoir to subsystem, 1 over kt times the difference in energy for the subsystem, whether it's in state 2 or in state 1. And now, just to make things sort of look a bit more symmetric, we say the difference in the exponent is just a ratio. And so now we have the probability is connected to this exponential, okay? It's not directly connected. We're looking at a ratio of probabilities, but there's some strong connection here between probability and this e to the minus 1 over kt times the energy of the state. The last thing I want to talk about in this lecture is the partition function. So before we get into that, let me just say we're going to make this definition. So 1 over kt, it doesn't look like that much to write, but it's up in the exponent, and just trust me, your life will be much better with beta. So beta is 1 over Boltzmann's constant times the temperature. Okay, so beta is an inverse temperature. And with that substitution, we can now write our probability ratio from up here. I'm just going to multiply both sides by the probability of state 1. And instead of saying state 2, I'm going to be a little more general and say state I. So some state of the atom, if I want to know the probability for some state of the atom, it's going to be the Boltzmann factor. Should have said that in the last section. The name this thing gets, because it's important it gets a name, it's the Boltzmann factor. So it's e to the minus beta e. I'm happier just saying it with a beta. Beta times the energy of the subsystem when it's in state I, times the probability of state 1 divided by its Boltzmann factor. Okay, so all I did was rearrange over there. And now I'm going to define this thing as 1 over z. Just as a warning, I am originally from the United States. I may call this thing a z. I mean z. Just bear with me, I'm getting better at it. But so we're going to define this whole thing as 1 over z, and if that seems like a strange way to define something, why don't I just call it z instead of 1 over z? We'll be there in just a second, you'll see why. Okay, so I haven't really done anything here. I've just rearranged an equation and given this a new name. It seems like all I'm doing in this section is renaming things, but we're going to get to some content, which will be good. Something we hadn't talked about before is that if you sum over all the possible states of your subsystem, the probability has to equal 1, right? In other words, if you remember the definition I gave you for probability, the number of ways your specific thing can happen over the total number of outcomes. Well, if you add up each specific way, at the end, that will be the total, so you'll have total over total. This is 1. Okay. So the total probability should be 1. So now let's take the probability in this form with this thing called 1 over z. 1 over z. Definitely wasn't going to say z there. And just plug it into this formula. Right, so if we sum all of these probabilities, we've got the 1 over z, and we've got the Boltzmann factor for each individual state. When we add them up, it equals 1. Now you see why I called it 1 over z. The 1 over z is a constant. It doesn't depend on I, so it gets to pull out front. And now just multiply both sides by z. The 1 becomes your z. Z equals the sum of the Boltzmann factors for every single state. Okay. Now this thing is important enough that it gets its own name and its own section of the lecture. It's called the partition function. Okay. So the sum on all Boltzmann factors, or rather the sum on the Boltzmann factors for all states of your subsystem, is the partition function. And I think essentially every book on statistical mechanics says the same thing, which I'm going to say to you now, which is, this is just a constant. Why are we making such a big deal out of it? And the answer is, it's a constant in that it doesn't depend on the state, right? It's a sum over all the states. But it does depend on beta, which, if you remember from 2 minutes ago, beta is 1 over kT. So in other words, the partition function depends on temperature. And it turns out that not only is redefining this in terms of beta going to make our handwriting a little easier, when you take derivatives of the partition function with respect to beta, you're going to get a whole host of quantities that are interesting in thermodynamics. So we won't go into them now. We're going to really spend the whole next lecture digging into what you can do with the partition function. So for the moment, just believe me, this constant that's not quite a constant turns out to be quite key for statistical mechanics. Okay, so there's our partition function, Z, obviously Z, not C. The last thing I wanted to mention is that you know from classical mechanics that energy is not really defined for a particular thing, only energy differences are defined. And that fact, right, so if I said, well, what's the potential energy of my coffee cup? Well, you say it's mgh, but there's nothing to stop me from making it mgh plus 100 joules. I've just redefined the 0 for h, right? So that doesn't change what will happen if I drop the cup, because when it lands, it'll have mg times 0, which was my original idea for where h was measured, plus 100 joules, right? So the change in energy will still be the same. That's sort of hinted at previously, because when we looked at something sort of well-defined, which was this ratio of probabilities, it was a difference in energies. But it's good to see for sure that we have respected the fact that you can change your reference point for energy without changing physics. So suppose we did this. We change our reference for energy. And now we're going to say that a state Si has a new energy E prime, which is the old energy plus this shift that we've done to our reference for 0 energy. Okay, we can calculate the partition function now. This is going to be Z prime is the sum on the Boltzmann factors, e to the minus beta, but now times the new energy with the shifted 0. So beta times the old energy plus E naught. This E naught is going to be in every single Boltzmann factor, so we can pull it out front of the sum. That means we can do the sum, which gives us the original partition function. And there's just this factor out front. So shifting the 0 point of energy just introduces an extra e to the minus beta E naught into our partition function. And when we calculate something physical, like the probability of a certain state being occupied, let's do it with the new definition of the energy 0, e to the minus beta naught times E plus E naught over Z prime. And we can pull e to the minus beta E naught out. I got carried away with my knots. I've got knots everywhere here. That doesn't belong there. And of course it takes out the E as well. We're going to fix this in the wrong color. Wow. Now you guys can see why I make the lecture notes before I lecture. Okay. So we've got P prime e to the minus beta E plus E naught. The e to the minus beta E naught we can pull out front. We already said Z prime is just e to the minus beta E naught times Z. So there's one of those out front. They cancel. And we get the original probability, which we knew should happen, right? We know that shifting the 0 point of energy should not change the answers to physical questions. And we see that it doesn't. But it's good to see exactly the mechanics for how that happens. Also, I just want to close by saying you should generally ask yourself, am I asking a physical question, right? Sometimes in physics, you build up a lot of formalism, and in that formalism, you can start to ask questions about the formalism that aren't physical, right? For example, if I said, what's the Boltzmann factor for this state? That's a totally valid question within the formalism of statistical mechanics, but I can't pull out my Boltzmann factorometer, right? I can't go measure the Boltzmann factor for something. What I can measure is the probability. And we know that physically measurable quantities should not change when we change the 0 point of E. But of course, things within the formalism can change. The Boltzmann factor will shift. The partition function will shift in a corresponding fashion.